Now that we have studied the predicate calculus and have some familiarity with well-formed formulas involving quantifiers, I thought it would be instructive and good practice to take a look at the formal versions of the Zermelo-Fraenkel axioms of set theory. I did drop a few enclosures in the hopes that it would make some of the formulas more readable. Also, the universe in each case is the class of all sets, so I didn't include mention of the universe in each of the axioms, as is commonly done. The first axiom that we'll talk about, it doesn't matter what order we do this in, is the axiom of extensionality. Zermelo himself took the meaning of equality of sets as identicality. That is to say, two sets are equal if and only if they're identical. The axiom of extensionality asserts that when two sets have the same elements, they are, in fact, identical or equal. This is what it looks like. For all x and for all y. So when these formulas get complicated, another way to think of that is for any given x and any given y, with no restrictions on the nature of x and y. Therefore, we're talking about all possible sets. So you can fix in your mind, pick an x and pick a y. For all z, z is in x if and only if z is in y. That says that x and y have the same elements. Elements are sets. So for all sets z, z is an element of x if and only if z is an element of y. That implies x equals y. So that is the symbolic form of the English sentence. If any two sets have the same elements, they are equal. You might be tempted to think this should be a biconditional. X equals y implies x and y have the same elements. That is true, but that's not part of the axiom because that's the definition of equality of sets. Next axiom, axiom of null set. This axiom asserts the existence of a set with no elements, which we call the empty set or the null set. There exists a set X such that it is not true that there exists a Y that is an element of X. In other words, X has no elements. We also might be tempted to rewrite that to look like this. It's more readable. There exists an X such that for all Y, Y is not in X. There is a slight problem with that. This symbol is not part of the language of the predicate calculus. So this technically is not a well-formed formula. It's an abbreviation for this well-formed formula. Now we could extend the language of predicate calculus to include this symbol. I don't know whether anybody does that or not, but it's probably better not to add symbols to a language that are not necessary. So there is a distinction between symbols that belong to the language of the predicate calculus, such as all the symbols in here, and symbols that are abbreviations for more complex well-formed formulas. Axiom of pairs. This axiom asserts that given any two sets, x and y, there is a set with only two elements, namely x and y. And there's no restriction that x and y can't be the same which would give you, rather than a set with two elements, two distinct elements, you get a set with one element. For all x and for all y, there exists a z. So given any two sets x and y, there's a set z for which the elements of z, for all w, w is in z, if and only if w equals x or w equals y. All the elements of z are either x or y. In other words, z has two elements, x and y. Axiom of power set. This asserts that for any set x, there's a set y, this will be the power set, whose members, z, are in fact subsets of x, but subset 2 is not part of the language. So we have to say whose members z have the property that the elements of z are also elements of x. That makes z a subset of x. So here's the subset condition. For all w, w's in z implies w's in x. Every element of z is an element of x. So this axiom says for all x, there is a y such that for all z, z belongs to y if and only if z is a subset of x. And again, we could adopt this symbol here as an abbreviation for all of this and write the axiom informally as for all x, there exists a y such that for all z, z is in y if and only if z is a subset of x. Axiom of Union. This asserts that given any set x, there's a set y whose elements are precisely the elements of the elements of x. That's quite a tongue twister, which is why I drew a picture. One thing to keep in mind is, you know, in high school, maybe you learned how to take the union of two sets. Here we are, in effect, taking the union of one set. We are taking the union of the elements of that set. They are subsets. The elements are sets. So we are taking the union of sets. We're taking the union of a set worth of sets. So x, I've drawn this here. This is a set x, and the circles, the open circles, are the elements of x. So this set x has 1, 2, 3, 4, 5, 6 elements. Each of the elements is itself a set, so it will have its own elements. So this element of x is a set of size 3, has 3 elements. Here's one of size 2. W here is an element of x. W itself has elements. I labeled one of them z. Now let's look at the axiom. What we're trying to do, the axiom of union says that the union of x, which you might think of as the union of the elements of x, or the big circles, their union is simply all the small black dots thrown into one set without the circles. You break down the elements of x and take out their elements and make a set that way. This is going to take a little, probably some time to think about before it becomes rather clear. This is not an easy one. For all x, so fix an x, there exists a y, that's going to be our union. Maybe I should have called it u to remind us, but most people wouldn't, so we'll leave it at y. Now, what about y? Well, it is the union, so it's the set containing the individual black circles, the black dots without the open circles. So, for all z, z belongs to y if and only if. What I've just said is basically we're defining y. For all z, z is an element of y. I'm about to tell you what the elements of y are. In other words, I'm about to define y. Z is an element of y if and only if there is a w, a set w, that belongs to x. It's right here. W, this open circle, belongs to x. And z is in w. So the element, z got into y by virtue of the fact that there's a set w, an element of x, and z is inside w. So z is precisely one of these dots. Okay, that was a tough one. Axiom of infinity. This asserts the existence of a set with an infinite number of elements. Now this is a little tricky. Excuse me for a second. This is a little tricky because there's no notion of infinite. We don't know what that means. Eventually we'll define that term, but it'll be quite involved. So the term infinite now is, we shouldn't be using it now because we don't know what it means, but it is commonplace to do so. So this is what it means to say there's an infinite set. There exists a set X such that the empty set is an element of X. So we know it's got one element. And for all sets y belongs to X implies y union, the set containing y, belongs to X. The first thing you notice is we're saying that if something belongs to X, something else does. Something different, something new. So we start with the empty set, and that provides a generator for more sets. The empty set is in X, therefore this is also in X, and this would in that case be the empty set union the set containing the empty set. Let me write that down here. The empty set belongs to X implies the empty set union the set containing the empty set. This is the empty set. Also belongs to X. How else do we know how to write this? 0 belongs to X implies 1 belongs to X. This, if you remember, this is the set, empty set, set containing empty set. And so this is 0, 1. I'm sorry, went too far. This empty set union, I jumped an integer, or I jumped a natural number. Empty set union set containing the empty set is just the set containing the empty set. When you take the union with the empty set, you're not adding any additional elements. And this is 1. Once 1 is in X, then 1 union, the set containing 1, is also in X. And this is 2. So you can see that the axiom allows us, the axiom is telling us that there's something in X, namely 0, and that since 0 is in the set, so is 1. Since 1 is in the set, so is 2, and so on. We get an infinite set. we can add some terminology here that might make this a little easier to explain. This, first of all, is a legal construction. If we have a set X, the axiom of pairs allows us to create this set, the set containing X, then the axiom of union allows us to form this. This construction is very important in set theory and has a name. The successor function, which I call script S, is defined on the class of all sets. The successor of a set X is this set. Again, this is legal. It's a real set because of the axiom of pairs and the axiom of union. Okay, S of X is called the successor of X. So what this tells us is that if Y is an element of X, then the successor of Y is also in X. That's how we get this chain that goes on indefinitely to produce an infinite set. So here it is rewritten. Any set that is closed under the taking of successors, which means that if you take any element in the set, its successor must also be in the set. That is called an inductive set. So what the axiom of infinity really says is that there exists an inductive set that contains 0, or the empty set. It should be the empty set, not 0, because we're going through the axioms of ZF set theory. We haven't defined the natural numbers yet, really. This is at the very beginning. So we want to refer to the empty set as the empty set, not as 0 at this point. So this axiom says that there is an inductive set and it contains the empty set as one of its elements. The set of natural numbers, 0, 1, 2, 3, and 4 on, and so on, it certainly contains 0 and is inductive, and it's the smallest inductive set that contains 0. Once you contain 0, you have to contain 1, and therefore 2, and therefore 3, and so on. Okay. The axiom of infinity is not saying that the natural numbers exist. It's saying that there is an inductive set containing 0. Therefore, this set will contain the natural numbers, but there's nothing here that says it can't contain other sets. All that's required is, besides containing 0, I did it again. Besides containing the empty set, is that whatever it contains the successors. Okay. The axiom of separation, also called the axiom of comprehension. Suppose that P of X is a property of sets. Okay. P of X could be the property that that X is non-empty, contains more than 5 elements, closed under successors, any property that applies to sets. Okay. The axiom of separation says that if we have a given set W, we can extract from W those elements that satisfy the property P of X and make a new set with just those elements. We are separating out the elements of the set that have the property. So as an example, suppose we start with the integers, And our property is that an integer is even. We can use the axiom of separation to pull out the even integers and form a new set, the set of even integers. Here's what the axiom looks like. For all w, there exists a y. This is the set we're constructing, such that for all r belongs to y. Again, we're defining which elements belong to y. R belongs to y if and only if R belongs to W, the parent set, and R satisfies the property. The axiom of replacement is similar to the axiom of separation, but takes it one step further. It's an upgrade, you might say. Here we have a property that depends on two sets. Equality would be a simple one. P of x, y is true if x equals y, be an example. Or x could be smaller than y or something. But anyway, it's some property of pairs of sets. But it must also be the case that given any x, there's a unique y that's for which this property holds for xy. Okay. So if the universe were the integers, for example, p of xy might be y equals x plus 1. Y is 1 bigger than 1. That fits. For every integer, there's a unique integer that's 1 bigger. Okay. Or y, this property could say y is the successor of x. Successors are unique. The axiom of replacement says that given a set W, we can produce a new set Z by replacing each element x in W by the unique y that makes this property hold. So before I read the formal formula here, let's look at an example. Again, p of x, y might be the property that y is the successor of x. So y is x union the set containing x. Then this axiom says that we can replace every member of a set W by its successor and get another set. So if W is the set 158, then the axiom says that the set 269 also exists. Those are the successors of 158. For all x, there's a unique y for which p of xy holds. That is the requirement for this axiom. It implies that for all sets W, there is a set Z such that, again, we're defining what's in Z. For all y is in Z if and only if there is an x such that x is in W and p of xy holds. So how does y get into the new set Z? It does so if and only if there is an element of the original set W and y is the unique element that makes this true, that satisfies this. So that's another one you may need to think about a little bit. The final axiom is the axiom of regularity, and you may remember me saying that this is a sort of a technical axiom. It's included to avoid certain behavior that we don't really want in our set theory. And this is a little bit of a tricky one also. Every non-empty set X contains an element that is disjoint from X. Remember, the elements of X, like any other set, the elements are sets. So it's conceivable. Here's a picture for X. Again, we use open circles to denote the elements of X. Each of those elements, including Y here, is itself a set and may have elements. The idea is that none of these black dots is also an open circle, and also an element of X. For all X, X is not the empty set, or what I'm really saying here is for all non-empty sets X. There exists a Y such that Y is in X, and for all Z, Z in X implies Z is not in Y. Okay. That's a bit of a tongue twister also, but difficult to get a hold of. So it takes some practice. There exists a Y such that Y is in X. So here's my Y, it's in X. And for all Z, Z in X implies Z is not in Y. Okay. So for all of the elements of X, Z is not in, for all the elements Z in X, Z is not in Y. So for all Z, Z in X means Z is one of these open circles. If Z is an open circle, then Z is not one of the black dots. Okay. The axiom of regularity, if you just stop there, you would say, well, why are we including that? Well, here are a couple of reasons. The axiom of regularity implies that no set is an element of itself. And that is good. We don't want sets to be elements of themselves. That's asking for trouble. Also, no sets A and B have the property that A belongs to B and B also belongs to A, that each one is an element of the other. That's another behavior we don't really like. And so the axiom of regularity forbids either of these bad behaviors. And we can prove that without too much difficulty. For part 1, no element belongs to itself. The axiom of regularity applied to this singleton set tells us this set has to have an element that is disjoint from the set. Well, this only has one element, A, so A has to be disjoint from the set containing A. So the intersection is empty. There are no elements in common between these two sets, A and the set containing A. Well, this set has only one element, A, therefore that element cannot be an element of A. A cannot be an element of A because then A would be an element of both of these. For part 2, we apply the axiom of regularity to the doubleton set, AB. Again, It tells us there's an element, which I'll call X in AB, that is disjoint from the set AB. Of course, the only elements of this set are A and B. So either X equals A or X equals B. If X equals A, we then have A disjoint from the set AB. So no elements in common between the set A and the set containing AB. Well, B belongs to this set, therefore B cannot belong to A. On the other hand, in a similar way, if X equals B, then these two sets are disjoint, and so B does not belong to A. So one of the two membership relations, A and B, B and A, one of them's always got to be false. They might both be false, that's fine. But what the argument we just gave said that there are two possibilities that have to occur, and one of them tells us this is false, the other one tells us this is false, which means these two cannot be true at the same time. Okay, if you're interested in the ZF axioms, if you found that interesting, you might want to read this over a few times, listening to the lecture a few times, try to help it to sink in. I'm not going to, when I teach this class at UCI, I don't ask the students to write down a ZF axiom. This is just for your own cultural information, and it helps you put the earlier material we did in perspective. It should make it look a little simpler. You know, we never, as we developed the theory of the predicate calculus, we never wrote any well-formed formulas that look like that. But you can see they do get complicated, and they do get hard to read. We're dealing with a primitive language here. There's an analog in computer science. You know, if you wrote your code in assembly language, which you can do, what might take 10 lines in a higher level language might take several hundred or thousand lines in assembly. It's lower level and therefore harder to read. Each command does less than commands at a higher level. We've got the same kind of thing going on here. So if you're interested, great. If you found the ZF axioms to be too stressful, you don't have to learn them because I will not test you on them. Okay. Now, that isn't to say I won't ask you the names of some axioms. I might say on a test, name 3 axioms of Zermelo-Frankel. You could name the axiom of union, the axiom of pair, the axiom of power set, the axiom of the empty set. You've got axiom of separation. You got 9 choices. But I'm not going to ask you to write down the well-formed formulas. Okay, that's just too much.